One element lights power plants and once lit a new age of warfare. Uranium. Same atom, two very different outcomes. Reactors that power cities and bombs that destroy them. Why does uranium win when it comes to power? Let's break the science, history, and reality behind the difference. At the heart of both nuclear reactors and atomic weapons lies the same fundamental physical process: nuclear fission. Inside the dense core of a heavy atom, like uranium-235, protons and neutrons are bound together by the most powerful force in the universe, the strong nuclear force. But for some large, unstable atoms, this bond is tenuous. A single, slow-moving neutron is all it takes to disrupt this delicate balance. When the nucleus absorbs this incoming neutron, it becomes highly unstable and tears itself apart in a violent burst of energy. This isn't just a simple split. It's a conversion of a tiny amount of matter into a tremendous amount of energy, as described by Einstein's famous equation, E equals mc squared. The result is two smaller atoms, known as fission fragments, a burst of heat and gamma radiation, and crucially, 2 or 3 new high-speed neutrons. These newly liberated neutrons are the key to unlocking fission's immense power. Each one acts like a subatomic projectile, capable of striking another heavy nucleus and triggering another fission event, creating a self-sustaining chain reaction. But for this to happen, the fissile material must reach what is known as critical mass, the minimum amount and density needed for the reaction to sustain itself. Below this threshold, in a subcritical state, too many neutrons escape, and the reaction fizzles out. At critical mass, the reaction proceeds at a stable, constant rate. But if the mass is supercritical, the number of fissions multiplies exponentially with each generation. This is where the path diverges. In a nuclear power plant, the goal is to maintain a state of perfect criticality. Engineers use control rods, which absorb neutrons, to fine-tune the reaction, ensuring a controlled, steady release of heat. This heat boils water, creating steam to turn turbines and generate electricity. But in a nuclear weapon, the goal is the exact opposite. By rapidly creating a supercritical mass, the chain reaction cascades out of control in a fraction of a second. The result is an instantaneous, explosive release of energy on an unimaginable scale. The same physics, but with two profoundly different outcomes. One, a source of sustained power, the other a tool of immense destruction. At the heart of both a nuclear power plant and a nuclear bomb lies the same fundamental force: nuclear fission. The difference between harnessing that power for electricity and unleashing it as a weapon isn't about using a different element. It's a tale of two vastly different approaches to managing the same phenomenon, the chain reaction. In a nuclear reactor, the goal is control, stability, and endurance. The process is meticulously engineered to maintain a state known as criticality. Here, for every atom that splits, exactly one of its neutrons, on average, goes on to split another atom, creating a perfectly balanced, self-sustaining reaction. To achieve this delicate equilibrium, engineers use control rods made of neutron-absorbing materials. They are inserted into the core to soak up excess neutrons and slow the reaction, or withdrawn to speed it up. A moderator, typically water, also surrounds the fuel, slowing down the fast-moving neutrons to the ideal speed for causing further fission. The result is a steady, manageable release of heat, generating electricity for years on end. A nuclear bomb, by contrast, is designed for the exact opposite: a violent, uncontrolled, and near-instantaneous chain reaction. The objective is to create a prompt supercritical state, where the number of fissions multiplies exponentially in a fraction of a second. This requires highly enriched material, typically uranium-235 or plutonium, concentrated to over 90% purity, far higher than the 3 to 5% used in reactors. This high density of fissile atoms is crucial for the runaway reaction. To trigger the explosion, conventional explosives are detonated around the fissile core, compressing it with unimaginable force into a supercritical mass. In that instant, a flood of neutrons begins the cascade. Instead of a steady release of energy over years, nearly the entire energy of the material is unleashed in microseconds. One process provides sustained power for civilization. The other creates a cataclysmic explosion. Control versus chaos. Two stars of the story: uranium and plutonium. Uranium occurs naturally. Reactors usually run on uranium. Plutonium doesn't occur much naturally. It's mainly created inside reactors when uranium atoms absorb neutrons. Both can fission, but they're used differently. Most commercial reactors use uranium that's been slightly enriched, only a small increase of the fission-ready isotope, because that makes for reliable, long-lasting fuel and a safe, controllable chain reaction suited to producing heat for electricity. A weapon needs a very fast runaway reaction. That requires special geometry and materials to make neutrons multiply extremely quickly, and materials with a much higher proportion of fission-capable isotopes. That geometry and concentration are what create an explosion, not a different magic element. So why did uranium become the backbone of nuclear power? While other elements can undergo fission, uranium was deliberately chosen by scientists and engineers. It possesses a unique combination of traits that made it the clear winner for large-scale energy generation. The decision rests on three core pillars: its surprising abundance, its ideal nuclear properties, and the decades of engineering that have made it a practical, reliable, and safe fuel source. Let's start with abundance. Uranium is actually more common in the Earth's crust than silver or tin. It's found in trace amounts all over the world, in rocks, soil, and even dissolved in seawater. This geological accessibility was the first critical factor that made a global nuclear industry feasible, ensuring a stable and geographically diverse supply chain that wasn't dependent on a single region. But abundance is useless without the right physics. This is where uranium's nuclear chemistry is perfect for the job. Natural uranium is mostly composed of an isotope called uranium-238, but about 0.7% of it is the all-important isotope, uranium-235. U-235 is fissile, meaning its atomic nucleus can be easily split by a slow-moving neutron. This split releases an immense amount of energy as heat, along with 2 or 3 more neutrons. Those new neutrons can then go on to split other U-235 atoms, creating a self-sustaining chain reaction. To make this process reliable in the most common reactors, the concentration of U-235 is increased from 0.7% to between 3% and 5% through a highly technical process called enrichment. This slightly enriched uranium is then formed into dense, stable ceramic pellets. The far more abundant U-238 also plays a crucial stabilizing role. It isn't fissile with slow neutrons, but it is fertile. It readily absorbs a neutron and over time transforms into plutonium-239, which is a fissile fuel. This means the reactor is constantly creating new fuel as it operates. This entire process is housed within meticulously engineered reactors, using control rods to absorb excess neutrons and manage the reaction's pace. This precise control, refined over decades, is what makes nuclear power generation fundamentally safe and allows us to turn a simple, heavy metal into a powerful source of clean electricity. Plutonium is produced in reactors and can be used as fuel or, under different circumstances, as material for weapons. That dual nature created political and technical debates about reprocessing spent fuel, safeguards, and international inspections. Myth: nuclear always equals weapons. Reality: the same physics powers reactors and explains weapons. But policy, engineering, and safeguards keep peaceful programs separate. Modern nuclear power emphasizes safety, regulation, and transparency. Uranium's place as a power source came from science, but stayed because engineers, regulators, and communities built an industry around safe, steady energy. If you want more deep dives, history, physics, or the ethics, tell me which angle you want next.